All right. Section 6, we begin talking about what's referred to as the natural base, or E. Now, I think the easiest way to explain this would be on your calculator. You'll notice how you have a log button, a common log button. But on a lot of calculators, you'll also notice how you have an LN button. Okay, what LN stands for is a natural log. All right. Now, before we get into kind of what the natural log is, we have to talk a little bit about the natural base. Now, some of you have probably heard of the number E. Basically, what E is E. It's not a variable. E just represents a number, approximately around like 2.78. It's an irrational number. It continues on forever. It doesn't repeat itself. Okay, but what we're going to talk about is basically what E comes from is an expression that is basically like an exponential expression. And because E is derived from an exponential expression, that means that its inverse would have to be a logarithmic expression. All right, but instead of representing it using common logs, we kind of create something entirely new as far as how we're going to represent it. So first we're going to talk about what the number E is, where it comes from, all that fun stuff. And then we're going to talk about how you solve different equations and problems that involve E or natural logs. Okay, so we're going to talk about the natural logarithm, and we're also going to talk about the natural logarithmic function as far as getting into functions. Now, basically, this is just kind of helping us understand what E is as far as E being a number. All right, compound interest formula would be this formula that's up here. All right, we've talked about interest a little bit, or growth models. We probably haven't talked necessarily about compound interest a whole lot, but basically what we're going to focus on is this interior part of that particular compound interest formula. All right, specifically what we have written down here, kind of without the T on the outside. Okay, this expression right here is how we end up understanding what E is. Okay, so if I flip to the next slide here, basically if you're going to take this function right here and you keep increasing the values of n, or you can think about n as almost being like x values. If we put x values in there and we keep increasing the x values, the quantity of the x value, I guess I should say, like say you start with 10, 100, 1,000, then you move on to 1,000,000, so on and so forth. What you'll start to understand is eventually that function kind of starts to, I don't want to say bottoms out, but it more or less kind of tops out, okay? And it really starts zeroing in on this value right here. Now, because we could keep putting an infinite number of values in for that n or in for that x, all right, it's impossible to tell where this number actually stops. It's going to continue to go on forever, all right? But once your numbers get high enough, you'll notice that these values in here tend to stay the same, all right? If you were to graph it on a calculator and really start to look at really large values of n or x, whichever you have them labeled, all right, you would see that they start to zero in or kind of top out at this 2.718 number. Okay, now because this number is derived from this type of expression up here, we just start to represent this as the number E. Okay, that's where this number right here comes from, is this expression. All right, but this number, we give it a special name and we just refer to as E, or we represent it like E. Now, E is a lot like pi in the fact that it doesn't repeat and it goes on forever and it's irrational. But I just wanted you to get the whole idea of where E comes from. Okay, it comes from this expression, and essentially what happens if you start increasing values of n to an infinite point. Okay, now the graph right here just kind of represents what's going on a little bit, as far as this would be where E would actually be that 2.718 number. Okay, if you look at another graph here, okay, if you use E as the base of your exponential function, all right, you're going to get something that looks like this line over here on the right. Okay, that's what happens if you use E as the base, and what you'll notice is that that's where E typically tends to come into play. Okay, so if we use E as the base of our exponential function, that means that the inverse of it would have to involve E as some type of logarithmic equation. Okay, now the important thing to remember here is if you're not 100% sure where e comes from or how we come up with it, that's fine. It's not really a big issue. What I'm more concerned about is you understand that e actually represents a number. Okay, so anytime e is a part of something, it's basically just like it's a number. Okay, so we had functions before of a logarithmic, or excuse me, of an exponential nature, like 2 to the x. 2 to the x is really not really much different than e to the x. Just remember, it looks like there's two variables when you see e to the x there, but e represents a number. Okay, so really what this is like down here is taking the number e, 2.718, 28, 1828, so on and so forth, and raising it to some particular power. Okay, so that's kind of how we're going to introduce and use this. Now, this section itself talks a little bit about how to graph this stuff. All right, the graphing idea for this really isn't much different than what we talked about before. Your easiest way to figure out a graph is probably use a graphing calculator. Now, it is possible to go ahead and use a table like is listed right here to come up with your values. The thing about it is, if you're going to find values using just random x values and developing a table, you're going to have to use a calculator to figure out what they're going to be as far as your output values or your y values, because they're going to end up being decimals. All right, so I'm not going to spend a whole lot of time. You are going to have to graph a couple of these on your assignment. If you want to just use a graphing calculator, fill it in, look at the table on your graph and get some ideas where some points are and graph it, that's fine. If you want to get accustomed to how you're going to do something like this, if you actually had to fill in values on your own, you sure could. All right, but it's one of those things where, again, I'm not going to spend a whole lot of time talking about how to graph these things, because you have all the resources you need to be able to graph them if you really had to. Okay, or again, if you wanted to fill values in for x, like 0, 1, 2, so on and so forth, you'd still have to use a calculator to evaluate what those numbers are actually going to be coming out. Okay, now here we kind of start to get into the bulk of what we're talking about. If your exponential function is e to the x, that means that the inverse of it would have to be some type of logarithmic function. Okay, so basically what you're doing here is, instead of just calling it log of something, we refer to it as the natural log function, which looks like this down here. So e to the x and the natural log of x are inverses of each other, or they undo each other. Okay, now the important thing to remember here is we read it as natural log of the x, but basically the base of a natural log function is e. Okay, so when you're doing this, like before when we tried to get logs to cancel each other out, like we said, if log base 2 of 2, if you had the same base as you did the number you're taking the log of, all right, essentially you just got 1. Or likewise, if I was writing something like this, if the number down here and the base up here were the same, it basically simplified to 2x. It's kind of the same idea, but when you're dealing with natural logs, it's e that undoes all that stuff. So if I had natural log of 2x, if I exponentiate it using an e, essentially that part would cancel out, and I'd be left with 2x. Okay, so just remember, like a common log had a base of 10, or there were other logs where we could basically just put whatever number we wanted to put in there for a base. With a natural log, the base of a natural log function is e, so to use some of those properties and kind of undo some of that stuff, you have to remember that using e is going to be the key to making some of that happen. All right, this gets into a little bit talking about domain and range. I'm not going to focus on that a whole lot. Just remember, with your exponential functions, if there's no transformation or translation being applied to it, the domain of your exponential function e to the x is going to be all real numbers. The range is just going to be from 0 on up in terms of a y. Okay, vice versa with the log, the natural log of x, or the inverse of e to the x. Okay, your domain becomes 0 and bigger, okay, or anything bigger than 0, because remember, you're going to have those asymptotes in there. Okay, a horizontal asymptote when we're talking about e to the x, and a vertical asymptote when we're talking about the natural log of x. So your domain goes from 0 this way when we talk about natural log of x, and your range would be all real numbers. Okay, again, just remember they're inverses of one each other, or basically the domain and range stuff is opposite of one another. Okay, now these are just some easy simple simplifications that we're going to make here. Now remember, the key here is just this. Okay? If you're taking the natural log, remember the natural log has a base of e. Now we said before, if the base and the number you're taking the log of were the same, essentially you just got 1 or whatever was left going on here. Well, in this case here, if the number down here, the base, is the same as the base up here, you just end up with the number that was in the exponent. So basically, to simplify, you just get this. Okay, likewise over here, okay, if the base down here and the base are the same, you're left with this times whatever would be left there. So 3x plus 3. Okay, again, the e and the natural log part essentially simplify to 1. It's the same thing down here. Okay, technically my bases on my natural logs are e's. That cancels out all this stuff and all that stuff, so I'm left with 2x plus x, which equals 3x. So those are just some kind of easy ones to get you introduced to the whole idea here. Okay, remember, the base of a natural log function is e. So if you take the natural log of e, the base and that cancel each other out, so you're just left with whatever up in the exponent in that particular case. On the converse side, or the opposite side, if the base of your exponential function is e and you have a log in the exponent, the e and the natural log cancel each other out, so you're left with 3 times whatever's left in your exponent there. Okay, the same could be said for letter C right there. Okay, so again, those are just some easy simplifications that we work with around here. Okay, now where e really comes into play is when we talk about compounding interest continuously. Okay, where you're going to use this formula, and there's a lot of application stuff that goes along with this. Okay, but basically A represents your final amount, P is your principal or whatever you're putting in there, R is the rate, which has to be expressed in terms of a decimal again, and T is the time in years that it's going to be put into something. Okay, so really all we're looking at right here is, what is the total amount for an investment of $500 invested at 5.25% for 40 years, and it's compounded continuously. Now, the key here is it's compounded continuously. All right, so we know we can use the formula that's listed right here. So my final amount, A, is going to be my principal, which is 500. Okay, E, okay, because E is just a part of the equation there. My rate, okay, is going to be, I have to make that a decimal. Okay, so it's going to be 0.0525 and then 40 up here. Now at this point, this becomes something that we just use our calculator for. So what I need to do is take 0.0525 times 40. Actually gives me 2.1. All right, so E, and your E, you have to go your second natural log button. All right, E to the 40th, or excuse me, E to the 2.1, sorry, not 40. E to the 2.1 gives you 8.16, then you're going to take that times 500, and you're going to get 4,083. So basically what that's saying is that your final amount will be $4,083 if you compound it continuously at 5.25% for 40 years. So again, it's just a matter of evaluate this part first, figure out what your exponent is, take E and raise it to whatever you get for that product, and then multiply by 500, and that'll give you your answer. So again, we're not really doing anything, outside of the box, so to speak. We're just showing how E can be used to go ahead and help us, deal with interest or application problems of that nature. All right. Now, the last thing that we're going to talk about here is E also plays a part when we're talking about half-lives and stuff in science. Now, this formula right here is just going to represent how we're going to go ahead and do this. Okay, so this is going to represent the n of t is just our function identification, I guess you could say it that way, and that's just going to represent the amount remaining after so many half-lives. Okay, n is going to be the initial amount that we put in there, n sub 0. Okay, e is just a part of the function, and k is the decay constant. Okay, now the decay constant is going to vary from problem to problem. So what we do with these is, first thing we have to figure out is what the decay constant is, and then we can actually go back and figure out what's going to happen or how long it's going to take to achieve some specific amount. Okay, so we're going to look at something like this. It says plutonium-239 has a half-life of 24,000 110 years. How long does it take for 1 gram of a sample to decay 2.1 grams? Okay, so again, half-life means if the half-life is 24,110 years, what that means is if you start out with 100 grams, after 24,110 years, you will be down to 50 grams. It decays and eventually erodes down to very small amounts. Okay, but what we need to do first is we have to figure out what K is. Okay, so what I'm going to do is I'm not going to think about any of the numbers that are in the problem. I'm just going to say if I'm supposed to get half my original amount, and we'll just say our original amount is 1, alright, I need to know, and my half-life number is that. I want to figure out what K is. So essentially what this is saying is after 24,110 years, alright, whatever my original amount was is going to be half of what it was to begin with. So I need to take something like that and I need to go ahead and figure out what K is, and then I can go back, and once I figure out what K is, I can go ahead and solve for T and figure out based on the amounts that I have going on here. So with all these problems, your first object is to find what K is. Alright, so what I'm going to do here is think about, well, the 1 in front here really doesn't matter. So I have 1/2 equals e to the negative k 24,110. Okay, now we talked about this before. To get rid of an e, I can take the natural log of it. Okay, so basically I'm going to say the natural log of 1/2 is going to equal, if I take the natural log of this side over here, the e is going to be gone, so I'm going to end up with negative k times 24,110. Okay, because remember, if I take the natural log of e to the negative k, the 24,110 right there, alright, this stuff is gone because my base would be an e down there, so my remaining expression is just whatever's in the exponent, and that goes back to some of the stuff we talked about in section 3 and section 4. Alright, now what I'm going to do here to make things a little bit easier to work with is I'm actually going to say that the natural log of 1/2 is the same as the natural log of 2 to the negative 1. You don't have to do it that way. Essentially you could use your calculator here at the end if you really want to. But what that allows me to do is to bring that negative out front and say I have negative natural log of 2 equals all this stuff. And then if I divide this over, okay, I can figure out what K is. So essentially I'm going to take the negative natural log of 2 and I'm going to divide it by 24,110, and I'm going to get basically a really, really small number, and it's going to be negative. But you'll notice I still have a negative over here, and because I still have a negative over here, what that means for me is that I can go ahead and basically make my answer positive. So what I get here is a 2.87 times 10 to the negative 5th. Or essentially I can take that and say that I'm going to have 4 zeros in front of it. And that is going to equal my K. Alright, so 0.0000287 is going to be my constant. Okay, now I'm actually going to write this up here a little bit. 0.00287 is my K. Okay, now what that's going to allow me to do is now I can go back, right, and I can figure out based on the numbers that I have here. Okay, I want to know how long 1 gram is going to take to decay to that. So if I'm supposed to get 0.1 at the end, my initial amount is 1. I know what K is, okay, in the problem, so we would say negative 0.0000287, alright, and then T right here would be the time that it takes to get there. So basically what I'm at right here is the same idea that I just did before. I'm going to take the natural log of both sides, alright, and essentially divide by the negative 0.0000287 to figure out what T is going to be. Okay, now again, it's kind of a two-part process. You have to figure out what K is before you can go back and solve for T. Alright, and I'm not going to go through the process of solving for T because that's really very similar in nature to how we solve for K in the first place. Okay, And your answer for something like this, if you want to go ahead and work it on your own, is probably going to be somewhere in the 80,000 range. All right, so it's going to take a long time for that thing to decay to that point. All right, so that pretty much covers everything. There wasn't a whole lot of work involved in this particular section, but there are some concepts you need to be aware of. And like I said, the main thing is just to understand the fact that the base of a natural log function is e, so we can use that e to help simplify things as much as possible. Okay, likewise, e to the x and the natural log of x are inverses of each other, and that becomes a big issue when we're trying to go back and forth between one or the other.